section of Unit 11, Day 9, Counting Principles. In calculating probabilities, we often need to determine either the total number of possible outcomes or the total number of successful outcomes. In many cases, the outcomes are easy things to count: red aces, blue marbles, coin flips, etc. But sometimes determining these values can be a little more complex. And we've already alluded to this somewhat. For example, Jimmy remembers the first 3 digits of Randy's number, but not the last 4. How many different possibilities are there? Well, there are 10 different digits, 0 to 9. We talked about this before. We talked about doing this dash system to help organize. So there would be 10 numbers that could go here, 10 digits, 10 here, 10 here, and 10 here. That's 10,000 different numbers. So Jimmy has a 1 in 10,000 chance of getting the numbers correct. Good luck, Jimmy. So as mentioned previously, the fundamental counting principle is a powerful tool to help us with problems like this. If you can choose one item from a group of m items and a second item from a group of n items, then the total number of the 2 item choices is m times n. The fundamental counting principle, FCP, allows for the use of the same item to be used more than once. For example, the telephone above, 2481212, is a perfectly fine result. It is for this reason that we multiply 10 times 10 times 10 times 10. Because 0 through 9 could be used for all of them. You can even have 2481111. You can't have repeats. But it's not always the case. Sometimes when we use a number or an item, it can't be used again. And we've alluded to this in class. For example, there are 4 people. We want to know how many different ways they can finish a race. A person cannot come in first and fourth. So you can't have 4 times 4 times 4 times 4. It doesn't make sense. One person, once the person places, they cannot be used again. So, a permutation is when order matters. Let's try a different problem. 4 bands are going to perform at the Friday night jam session. How many different ways can they be scheduled? Could the schedule be arranged? So, the way I make sense of this is 4 different bands should go first. So once played, 3 bands can go second, 2 bands, then 1. So that's 4 times 3 times 2 times 1, which is 24 different ways. In mathematics, we multiply n times n minus 1, which is 3, times n minus 2, which is 2, times n minus 3, and we keep going. And we call that a factorial. And that exclamation point actually means factorial, n factorial. So 6 factorial is 6 times 5 times 4 times 3 times 2 times 1, 720. 3 factorial is 3 times 2 times 1, 6. 1 factorial is just 1. And by definition, 0 factorial is 1. That's very important to remember that one. This throws people off. Remember, 0 factorial is 1. So, band problem has a few important characteristics that our earlier fundamental counting principle didn't have. No repeats, no item used more than once. And the order of the arrangement makes a difference. So if your favorite band is playing and they're playing first, you could leave after that if you so chose. But if they were playing last, you'd have to stick around for the whole thing. So order matters. When these 2 conditions are involved in the arrangement, it is called a permutation. When does order matter? That's an important question. Order matters when the sequence means something. Order matters when the value or meaning of the location is somehow different from other locations. When order matters, 1, 2, 3, 1, 3, 2, and all these are all different. So think about it. These are your locker number. They're going to be located in different places, different floors, so forth. If order didn't matter, all of these are the same arrangement for the situation. So, in the below examples, note no items can be used more than once, and order matters. Thus, these are the examples of permutations. If you have 4 books, how many different ways can you arrange these books, assuming the order matters to you? Well, that's 4 times 3 times 2 times 1. 24. There are 10 different people in a race. How many can finish first, second, and third? Well, our order obviously matters because there's a ranking, first, second, third. So, any of the 10 people could come in first. That leaves 9 people that come in second, and 8 people that come in third. That's 720. Now, the above method to calculate permutations is very intuitive, but very effective. There's also a formula that summarizes exactly what we've been doing. So n is the total number of elements. Okay? That's where the 10 comes in, right here. We know there's 10 people, for example. R is the number of items being chosen. So in our second example, R is 3, because we have first, second, and third. And then, and 10 minus 3 is 7. So there you go. We would read it, the permutation of 10, choose 3. That's how it technically is read. Okay, right here. 10, choose 3. We use a P for permutation. So really what we're doing here, and you don't see it, but what we're talking about is 10 times 9 times 8 times 7 times 6, 5, 4, 3, 2, 1. Divided by 7 times 6 times 5 times 4 times 3 times 2 times 1. Well, notice, all these cancel. And what are we left with? 10 times 9 times 8. Now, sometimes order doesn't matter. Teacher wants to pick 2 students to get textbooks from the other room. If there are 5 students, how many groups can be formed? What is different about this question from the permutation question? Order doesn't matter. In other words, it's not like you're sending 2 kids and one is the supervisor and one is the worker. They're equal, have equal status, equal power. It doesn't matter if Jimmy walks out before Joan or Joan walks out of the room before Jimmy. It makes no difference. You're both being chosen. It doesn't matter who's picked first. They're doing names out of a hat. Okay? Mike and then Joe is the same as Joe and then Mike. This is known as a combination, as opposed to a permutation. So again, no item is used more than once. Let's say I was picking out of the 5 kids, let's pick the names out of the hat. If I pick Mike, and I put Mike back in the hat, I pull Mike out again, I can't send Mike as 2 people. He's only one person. So there cannot be repeats. But order makes no difference, technically, of the arrangement, but order of the arrangement makes no difference at all. Picking 1, 2, 3 is the same as 2, 3, 1, or 3, 2, 1, or 2, 1, 3. From From 7 students, a committee of 3 is being formed. How many of the groups of 3 can be formed? So, based on what we did before, we would say 7 times 6 times 5, which is 210. But that is not the correct answer, because we have a lot of the same groupings in different orders, and we've got to get rid of those groupings. So we'll come back to this after we learn the formula below, but we'll find out how that is not right and how to fix it. The next one, 5 books on the table, needs to pick 2 to read for an English assignment. How many different ways a group of 2 could be formed? Well, again, 5 times 4 equals 20. But if the order in which he reads them does not matter, it can't be 20. If these were permutations, these would be our answers. Well, they're not. They're combinations. So let's find out what happens. Okay? We've got to get rid of the duplication. So n is the total number of elements. R is the number being chosen. Notice the slight difference to the permutation formula. We're also going to divide by r factorial to take out any duplication. So let's go back up to redo our original ones. If I had 7 factorial divided by 7 minus 3 factorial, that would give me, again, if it's a permutation, 7, 6, 5, 4, 3, 2, 1, divided by 7 minus 3, that's 4 factorial, 4, 3, 2, 1, which leaves me with what? 7, 6, 5, 210. But with this new formula, we're going to add 7 factorial, 7 minus 3 factorial, but then we're going to add a 3 factorial right here. We're going to divide by 3 factorial. So what does that look like? 7, 6, 5, 4, 3, 2, 1, divided by 4, 3, 2, 1, but we're also going to divide by an extra 3, 2, 1. 3 factorial. Now, when these all cancel, that's well and good. But 3 times 2 times 1 is 6. So what are we left with? Just 7 times 5, which equals 35. So if we came back up here and divided by 6, right, get rid of that, we would get 35. So let's go back to our other one. If we had 5 factorial divided by 5 minus 2, which is 3 factorial, but then an extra 2 factorial, that would be 5 times 4 times 3 times 2 times 1, divided by 3 times 2 times 1, divided by also a 2 and a 1. So these cancel, and 2 goes into 4 2 times, which would give us 5 times 2, which is 10. Again, we came back up to this original one and divided by the 2 factorial, which is just 2, we would get 10. So that's the main difference between permutations and combinations. Last bit. Determine the following are fundamental counting principles, permutations or combinations. In a race, how many ways can 3 people finish? Well, there can be no repeats and order matters. That makes it a permutation. How many 4-digit passcodes are possible? Well, that's when we do 10, 10, 10, 10. Order matters, but we can't have repeats. So that's just the fundamental counting principle. In how many different ways can a two-person committee be selected from 10 people? Since there's no order, and it doesn't matter who's picked first, it's a combination. Now, if I said there was going to be a lead partner and a second partner, that would be a permutation. 5 quizzes on a multiple choice quiz. Each question has 4 possible answers. How many possible ways could you answer the question, the quiz? Well, in that case, we have 5 questions, and there's 4 possible answers for each. That makes it a fundamental counting principle problem. E, 20 old video games are in a bin. Science says pick any 4 for $5. How many different groups of 4 are possible? Well, it's not going to matter what order you pull them out. It's a combination. 4 bands are performing. How many different ways can they be arranged? That's a permutation because the order of the bands matters. Now do the math on these. Well, the first one is going to be how many ways can 3 people finish a race? So that's permutation, 3 people and 3 ways. That's going to be 6. So mathematically, remember that's 3 factorial, which is 3 times 2 times 1, divided by 3 minus 3 factorial. And what do we say? That's 0. But remember, 0 factorial is 1. So that's 3 times 2 times 1 is 6, divided by 1, which is 6. B. The passcodes, wrote it up there. That's just 10 to the 4th power, which is 10,000. Okay? The two-person committee. Well, again, it was permutation. 10 people being chosen 2 ways. So that's 10 factorial divided by 10 minus 2, 8 factorial. I lied. We said that was a combination, didn't we? Order doesn't matter. So instead of that, we also have to divide out an extra 2 factorial. So the nice part about this is we have 10 times 9, and then the 8, 7, 6, 5, 4, 3, 2, 1 is all going to cancel with the 8, 7, 6, 5, 4, 3, 2, 1. Now, if this is a permutation, it would be 10 times 9, 90. But we had an extra little 2 times 1 down here. So 10 times 9 is 90, divided by 2 is 45. D, we said that was just 4 to the 4th power, which is 1,024. E, that's combination again. 20 games chosen 4 ways. So that's 20 factorial over 20 minus 4 is 16 factorial, but we also have to have that extra 4 factorial. So mathematically, that's going to be 20 times 19. Now I'm just going to save all the space because you know 18 down to 1 is just going to cancel, right? That's going to cancel here. But we're also going to have that extra 4 times 3 times 2 times 1. So on the top, we have 20 times 19 divided by 24. And that works out to be 4,845. It's a lot of different video game combinations. And last but not least, we have 4 people, 4 bands, playing 4 ways, being chosen 4 ways, and permutation because order matters. This is very much like A, okay, where we're going to have 4 times 3 times 2 times 1 divided by 4 minus 4 factorial, which is just going to be 1. So it's really just 4 factorial. So whenever the numbers are the same on the permutation, it's just that number factorial. So 6 permutation 6 is 6 factorial. 9 permutation 9 is 9 factorial. That's it.